Hey guys, it's Ms. Johnson, and I'm here to bring you the first part of our lesson for chapter 6.3, section 6.3. We are talking about binomial and geometric distributions in 6.3. So two different distributions of random variables and what makes something a binomial distribution and also what makes something a geometric distribution. So today we're just going to talk about binomials. So binomial distributions. Here's kind of the definition of a binomial setting. So a binomial setting arises when we perform n independent trials of the same chance process and count the number of times that a particular outcome or success occurs. Here are the four things that you have to look for a binomial setting. The first and foremost thing that makes it easiest to spot a binomial setting is that B. It needs to be binary. That's where you get the term binomial. Binary means you have a success and a failure, and that's it. So, for example, a true and false question. You've got one success, one failure. You could make a multiple choice of binomial setting saying, did they get the answer right or wrong? Okay, so when you are looking at things in terms of only success and failure, then you're looking at a binomial setting, okay? Independent, the trials must be independent of each other. So when you, again, I'll go back to true and false. When you look at question number one being true and false, question number one has no bearing on question number two, and that has no bearing on question number three. All of those questions are independent of each other. Then the number part, the number of n trials must be fixed in advance. So for example, I may say, what's the probability you get 5 questions correct on a 10 question true or false test? So that 10 question true or false test is fixed before you start the experiment. That's before you end up doing any of the work. Okay, so you have to know the number of trials. And then same probability. Each individual trial has to have the same probability of a success. Okay, so they kind of give you a fun little acronym here, BINS, they call it. Check the BINS. That's what you can tell yourself, or that's what you can use to remember the characteristics of a binomial setting. So is it binary? Are the trials independent? Do you know the number of trials, and do they have the same probability? So if you like little fun tricks like that, there you go. So let's just talk about identifying those things in this question. It says, determine whether the given scenario describes a binomial setting. Justify your answer. So the first one, genetics says that genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Count the number of children with type O blood. So let's just go through and check the BINS, because the question is determine whether it's a binomial setting or not. So for B, is it binary? And that is a yes, because it's either type O or not. So there's success, failure, okay? How about the I? Independent, and that is a yes. From one child has no bearing on the next child's blood type, okay? Each child is separate from the next. N, a fixed number, and that is a yes, because 5 children, you're told there are going to be 5 children before you start. And then S, same probability, and that is also a yes. Boom, right there. Okay, so the answer here is yes. This is binomial. Okay, let's try the next one. Shuffle a standard deck of 52 playing cards. Turn over the first 10 cards one at a time. Record the number of aces you observe. All right, so let's check the BINS. B, that's binary, meaning success or failure. And the answer there is yes, because it's either ace or not. There's your success, there's your failure. I is independent. And check this out. This is a big fat no. Taking a card out, here's why. Taking one card out and keeping it out changes the probability. Anytime you start changing the total number of things that you have, then they're not independent anymore. Okay, so like we start with 52 cards, we turn over one card, then we only have 51 left. So now the probability for the next card is out of 51 instead of out of 52. Doesn't even matter what total you're or what success you're looking for. The fact that you changed the total is enough to make them not independent. So this is a no, not binomial. Sorry, not binomial. All right, let's try this one. Shuffle a deck of cards, turn over the top card, put the card back in, shuffle again, repeat this process until you get an ace. Count the number of cards you had to turn over. Okay, so B, let's check our bins here. B, binary, yes. Same type of question. This is a yes because it's either ace or not. Now, here's where it's different. You're going to turn over the top card, put the card back in, and shuffle again. So these ones are independent. Yes. That is a yes there. And that's because you put the card back. So that's good. So then let's talk about N. Repeat this process until you get an ace. Repeat this process until you get an ace. That is the problem here. Since you are repeating this process until you get an ace, that is not a fixed number of trials. You don't know how many times you're going to try. Okay? Since it's not a fixed number of trials, this is not binomial. And you can stop with your bins checking. Okay? All right, so let's talk about a binomial distribution. It says the blood type scenario in part A of this example, of the example we just looked at, is a binomial setting. So if we let X equal the number of children with type O blood, then X is the binomial random variable, okay? So X is like the number of successes you're gonna get, basically. That's what's happening there. So X being the number of successes, that when you make a binomial or a probability distribution, like if you line these things up in a table and you put, the numbers, so it could be 0, 1, 2, 3, 4, and 5, and you put the probability down here, that's your probability, if I could right there, that's your probability distribution of that binomial distribution. So the count of successes X in a binomial setting is called the binomial random variable. The possible values of X are 0 all the way up to the total number of trials. For the children with type O blood, in the last example, it's either 0, 1, 2, 3, 4, or 5. The probability distribution of X is called a binomial distribution. Any binomial distribution is completely specified by two numbers: the number of trials N, the number of probability of each success P, and then the number of successes X is what the table is made up of. All right, so let's talk about how to actually calculate those probabilities. So it says each child of a particular set of parents has a probability of 0.25 having type O blood. We're going back to that same example. We're looking at 5 children. So there's your P, there's your N. Okay, what is the probability that exactly 1, meaning X equals 1, of the 5 children have type O blood? So the probability of X equaling 1, exactly 1 child having type O blood. All right, so here's where life gets kind of funny. So you have to factor in 3 different pieces. 2 of the pieces make a lot of sense. The third piece is kind of a struggle for some people, but let's just talk about this second and third piece. This second piece is the probability that 1 child has type O blood, and that is 0.25 raised to the first power. You can't just factor in the successes, though. That's where it gets tricky. You have to factor in the successes and also factor in the failures. So the last part here is for children who do not have type O blood, okay? And that is the 0.75 raised to the fourth power. So your probability of success was 0.25, which means your probability of failure was 0.75, because that's all you're looking at. You have a success and a failure. So to find the failure, you do 1 minus, just like we looked at those complement probabilities back in chapter 5 and way back in like chapter 1. So 0.25 is my probability of success, 0.75 is my probability of failure. That accounts for all 5 kids. 1 success, 4 failures. So raise that to the fourth power, raise that to the first power. Now, here's where things are a little bit tricky. This first piece, see that 5 right there? That 5 right there is the number of ways to get 1 out of 5 with type O blood. So if you've got 5 children in the family, there's 5 different ways that you can have 1 success. It could be the first child, it could be the second child, the third child, the fourth child, or the fifth child. There's 5 different ways that you can do that. So that is a piece that people often forget about. You have to factor in that piece right there. So the number of ways to get K successes on N trials, okay? Then you factor in the probability of success, and the probability of success is raised to the K power. I'm not sure why they used K here. They use X up here, but now they use K in the formula, but that's okay. And then the probability of failure is basically the probability of failure raised to the number of failures, okay? So you raise it to the number of failures. The probability of success, you raise to the number of successes. Okay, and then you need the number of ways. Now, that number of ways is really easy when you're only picking 1 success. But if you have more than 1 success, that gets a little bit trickier. So I'm going to take you down a trip down memory lane, and we are going to revisit the concept of combinations. All right, so this binomial coefficient comes into play. That binomial coefficient comes into play by using combinations. So if you can think back to Algebra 1 or Algebra 2, I know we teach it at Algebra 1 if you took Algebra 1 in 9th grade, but a lot of you took Algebra 1 in 8th grade, so I'm not sure if you did it. But you should have seen combinations in Algebra 2. So this is the combinations formula. That's what this is. And the combinations formula tells you the number of ways you'll get K successes out of N trials. That's what it is. It's K successes out of N trials. So remember back to this little guy, the exclamation point being factorial. Factorial is when you take the product of all the numbers from N down to 1. Okay, so I'm just going to do a really brief example down here at the bottom. Let's say I had the combination of 5 objects choosing 2 of them. So the combination of 5 objects choosing 2 of them is going to be 5 factorial divided by 5 minus 2 factorial with an extra 2 factorial. Okay, I always do my parenthesis one first and then the solo one after. It doesn't really matter. Obviously, we can multiply in any order. But here's what that looks like. Do the subtraction. This is just 3 factorial, right? So then I've got 5 times 4 times 3 times 2 times 1 on the top. On the bottom, I have 3 times 2 times 1, and then I have another 2 times 1. That's what that factorial is. And again, hopefully this is a refresher for you. Hopefully you've seen this before. It may have been a long time, but you should have seen this before. So here's our factorial. Now, this is the lovely part about factorial. I can cross out 3 over 3, goes away. 2 over 2 goes away. 1 over 1 goes away. I don't need this one because dividing and multiplying by 1 doesn't change anything. I can also take 4 divided by 2 and call it 2. Again, I'll say that again because I went over that kind of fast. 4 divided by this 2 is 2, so all I did was really reduce that. I'm left with just 5 times 2, which is 10, okay? Here's the other thing that I want to show you. The other thing that I want to tell you about is, obviously, this is not going to be super reasonable to do on a test, but thankfully for us, just like every other thing in this class, we have fancy machines that do NCR for us, okay? So NCR on a calculator. When you are trying to do the combination of something on your calculator, here's what it looks like. Your keystrokes would be, you type in your N. So in this case, you type in your N. Then you hit your math button. You arrow over to probability. So PRB. Oops, undo. That's supposed to be a P. PRB. And then for me, it's option 3, but you're looking for NCR. Hit enter on that. And then put in your K or your number of successes and then hit enter again. Okay, so there's your keystrokes. Write those down. You can also find them in your book. There is a page in your book that will tell you how to calculate those. Page 436 goes through that calculation. And again, this is just the NCR piece. This is just this first part, okay? The first part of that formula. Then you still have to do the probability of successes raised to the number of successes times the probability of failures raised to the number of failures and multiply it all together. So here's the whole thing. This is the kind of thing, you guys, that you'll see on your AP exam formula sheet. So you will see this, not the description. It doesn't tell you, it's just going to say the word binomial probably. But on your AP exam formula sheet, you'll see this. Okay, you get these two things. I'm pretty sure you get the combinations. I'll check on that, but I'm pretty sure you do. But yeah, that's the kind of thing that you'll see on your AP exam formula sheet. So it's all great and fine to have that formula on the formula sheet, but if you don't know how to type this stuff into your calculator, then it becomes tricky. And really, you could work it out yourself, just like I did with the 5C2. You could draw out your factorial. It just becomes a problem when your N gets really big. Like, what if you're doing a trial of 30 or an experiment of 30 different trials? You don't really want to do 30 factorial in your calculator. 30 times 29 times 28 times 27. That would take a long time. So it's nice when you know the keystrokes to find that NCR in your calculator. All right, so let's do one. It says genetics says the genes, blah, 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 0.25, have 5 children. Same example. Here we go. Let X equal the number of children with type O blood. Find the probability of X equaling 3. And then interpret, always our favorite. That means write something out. Write on some sort of concluding statement. Okay, so let's start with the probability of X equaling 3. Here's what it looks like. This is going to be 5 children choosing 3 successes. The number of ways you have 5 children choosing 3 successes. And by the way, there was a little note back there that I kind of skipped over. This is not a fraction. Notice I do not have a fraction bar in there. That is notation for combinations. Okay. It's not a fraction, it's combinations. Okay, moving on. So then probability of successes, that's 0.25 times itself 3 times for the 3 kids that get the type O blood and have that success. Then probability of failure. If 3 kids have a failure, that means that, or I'm sorry, if 3 kids have success, then 2 kids have a failure. Or in other words, that's 5 minus 3, which is the second power. So number of ways to pick 3 successes times 3 successes times 2 failures. That's what's happening here. If I plug all this in, 5C3 is again going to be 10. And that's not a coincidence in 5C2. It's because 2 plus 3 equals 5. Let that sink in for you. But they'll be the same number. When you take the combinations of 2 things where the successes add up to the total, they're the same number. There you go. Fun fact for you. 0.25 to the 3rd power, 0.25 raised to the 3rd is 0.015625. And then 0.75 raised to the second power is 0.5625. And then I want to multiply all those together. So 10 times 0.015625 times 0.5625. There you have it. This is going to be 0.0879, or you could say 0.088. Okay, probability of x equaling 3. There's your probability. Now, context. Some of you missed this part on your Chapter 5 test. So make sure that you're writing out what this means in context. And I know it doesn't always say interpret this value. The question doesn't always say that, but I can promise you that the AP exam wants to see you write out some sort of concluding statement in the context of the question. If you don't do that, you will get a P on that free response question. I can promise you that. Okay, so here is my reflection statement or my conclusion statement in context of the question. There is approximately an 8.8% probability that exactly 3 children out of 5, there's your context, children out of 5 will have type O blood with P equaling 0.25 for each trial. There you have it. Okay. So write out some sort of statement. You have to include your context. They're going to want to see that, I can promise you. Let's try another one. So now it says the preceding example tells us that each child of a particular set of parents, 0.25 type O, 5 children. Should parents be surprised? This is important to note because some of you forget to actually answer the question. So should parents be surprised is the actual question. Make sure you answer that at the end. You're going to have to find a whole lot of calculations to get there, but you need to actually go back and answer the question. So should parents be surprised if more than 3 of their 5 children have type O blood? Calculate an approximate probability or an appropriate probability to support your answer. Okay. So if you are looking for a probability of more than 3, that means you want the probability of x being greater than 3. That's going to be the same thing in this case as probability of x equaling 4 plus the probability of x equaling 5. So what that means is you have to put in this equation 2 times. So for the probability of x equaling 4, I have 5 objects choosing 4 of them, times 0.25 to the 4th power for 4 successes, times 0.75 to the 1st power for 1 failure. 4 successes, 1 failure. That's the first formula. Then to that, I need to add the second formula, which would be 5 choosing 5 times the probability of 5 successes times the probability of 0 failures. So you've got 5 successes and 0 failures there. So I'm going to go ahead and plug these 2 things into my calculator to give us our probabilities here. And when I plug the first one in, I end up with 0.0146, and it keeps going on and on and on. And then the second one was 0.000976. Obviously, getting all 5 successes is a pretty rare thing. So if I put those 2 things together, I end up with 0.015625 when I add them. So here's my reflective statement. Here's how I would interpret that or write that out. I would say the probability of more than 3 children having type O blood, is 0.015625, but notice I haven't addressed that question yet. So, yes, this would be surprising. When you have a 1% chance, that's a pretty low chance of something happening. A 1.5% chance technically here. That's a pretty low percent of something happening. So yeah, I would definitely say that that's a surprising result. All right, so now like everything else in our class, there are formulas and ways to do things by hand, and then there are also methods on our fancy machines, meaning our TI-84 calculators, to do them on the calculator. So I want you to think back to chapter 2 when we were doing normal distribution, and we would do normal CDF to find a cumulative probability of a normal distribution. Just like we could do that for normal distribution, we can also do that for binomial distribution. So you find this option of binom PDF and binom CDF in the same distribution menu on your calculator. So binom PDF and binom CDF. Now here's the difference between the PDF and the CDF. PDF is when you want the probability of an exact value. So that's when you're just looking at one value. CDF is, the C is for cumulative. So the C is when you're looking for a cumulative set of values, meaning there's a bunch of different K values that are successes for you. So PDF is when you have X equaling something, and CDF is when you have X is greater than or X is less than or things like that, okay? Now, we have to be a little bit careful about our inequality symbols. So you can see down here in the second window, if we want X is greater than or equal to 3, we are always measuring the things underneath. We're always measuring the things to the left. So we want to take 1 minus the X is less than or equal to 3. So that's going to change a little bit how we type it into our calculator, okay? So we just want to always think about what is the cumulative probability underneath what we want. If you're looking at a less than or equal to probability, then you're great. Then you just do that number and that's your probability. But if you're looking at something that's greater than, then you have to put in the less than probability and take 1 minus that number. Okay, so this is just our steps to finding the binomial probabilities. The first step is to state the distribution and the values of interest. The values of interest are how many trials, what's the probability on each trial, and then what's the number, it says, in the value of the variable clearly defined. So that's your X. What's your X? Is it equal to, is it greater than, is it less than, greater than or equal to, less than or equal to, whatever it is. Then step 2 is to perform the calculations, and you have to make sure you show your work. So you can either use the formula, like we just did a few times in the past couple examples, or you can use binom PDF or binom CDF, but this is the kicker. You have to clearly label each part of the input, okay? And then you always want to make sure that you answer the question that's asked. So this labeling piece, go back, think back to chapter 2 when we did normal CDF and we had to list lower and whatever it is, and then upper and whatever it is. That is going to be the same thing here. This is normal CDF, okay? When we did the normal CDF, that's what we would do in our parentheses. We would list out the lower bound, the upper bound, and then we'd have the mean and the standard deviation, whatever those may be. So you have to clearly label what those parameters are. For binom CDF, you've got the trials, or you could say number of trials. You've got the probability of success And you could probably just say probability and that would be okay. And then you've also got the number of successes. Those are the 3 values of interest when you're putting things into your binomial CDF. So making sure that you label those values of interest when you're showing your work on a free response question, that's going to be really important. If you just listed this, this, and this without the labels, I can promise you they're not going to give you full credit on the AP exam. So let's do one together. It says a local fast food restaurant is running a draw 3, get it free lunch promotion. After each customer orders, a touchscreen display shows a message, press here to win a free lunch. The computer program simulates one card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer will have to pay the bill. So on the first day of the promotion, 250 customers placed lunch orders. Find the probability that fewer than 10 win a free lunch. Okay, so here's what we know. First of all, we need to make sure we're looking at a binomial setting. So binomial setting, okay, I know that I've got the B, meaning success or failure. B is good. It's either free lunch or not. I guess I could put that. Free lunch or not, that's my success or my failure. Free lunch or not. I know that the I, they're independent. Each person is independent. They independently draw and they don't cross over and they don't remove any numbers from the system. It's not like they're taking a 3 out and then that 3 is gone. You know what I mean? So each person is independent. Good, check. N, fixed number, 250 trials. And P, probability is the same. I know that the probability is going to be 3, or I'm sorry, let's take that back. Drawing a 3 from a standard deck, which there are 4 3s in each deck. So drawing a 3 from a standard deck is 4 out of 52. Okay, so the probability is the same. So I'm checked off there. I know that I'm looking at a binomial setting. The next thing I would think about, so I want the probability of x being less than 10, which means I need the probability of x equaling 0 plus the probability of x equaling 1 plus the probability of x equaling 2 all the way up to the probability of x equaling 9. Okay, I'm adding all those things up. Now, what that means is I would have to do the binomial distribution formula 10 times over. I'd have to do it for 0, for 1, for 2, for 3, for 4, 5, 6, 7, 8, and 9. I don't know about you, but I don't really want to do that probability distribution formula 10 times. That does not sound like fun to me. So I am going to use my binomial CDF. And the reason I'm using CDF in my calculator is because I have a cumulative distribution of 9 all the way down to 0. Now, the good news here is I'm looking at less than. I'm already to the left. I'm already going underneath that value. So I don't need to mess around with the 1 minus part. That's the good part. I'm already looking at the left-hand side, or in other words, going down, not going up. So I don't need to worry about 1 minus, but I do need to be really specific about how I list out my values. So I know that, here are the things that I know. I know that the number of trials is 250. I know that the probability of each trial is 4 out of 52. And I know that the number of successes is going to be 9. Successes is going to be 9 on down. So my binomial CDF looks like that. And now I'm going to go ahead and type it into my calculator. So in my calculator, I go second distribution. I go to binomial CDF. Now in your calculator, it's down near the bottom. So you're going to have to scroll a little bit. For me, it's option B. It's actually after all the number options, and then I get to option B. So binomial CDF, number of trials is 250. My p-value is 4 out of 52. I like to put fractions in parentheses. It just makes sure that I know I am including everything all together and I'm not leaving out any, subtraction or things like that. So, or I mean division, whatever. So I put my 4 out of 52 in parentheses, and then I'm going to go down and I'm going to paste it. And here's my probability. So my probability of x being less than 10 equals 0.00613 roughly. So then I go back and I answer the question in context. So on the first day of the promotion, 250 customers place lunch orders. Find the probability that fewer than 10 of them win a free lunch. So the probability that fewer than 10 customers win a free lunch I should say fewer than 10 out of 250 customers win a free lunch is 0.006, with each customer's probability being, I'm running out of room, sorry, being 4 out of 52. Something to that effect. All right. Okay, so here's part B to this same example. So it says, in fact, only 9 customers won a free lunch. Does this result give convincing evidence that the computer program is flawed? So here's the thing. If only 9 customers won a free lunch that day, what that means is my X value was equal to 9. So then here's the other piece of information that we know. We know from part A, the probability that X was less than 9, or so I should say X is less than 10, that's what we did. X is less than 10 was equal to 0.006, which is a really, really low probability. So since the probability of getting less than 10 winners is so low, and we're even only looking at 1 out of those numbers that are underneath the 10, so that would be an even lower result, it's such a low probability, that shouldn't happen. Since it's such a low probability, it shouldn't happen like that. So because the probability of getting less than 10 is so low at, and you can even say what it is, 0.006, we believe, or I should say, we have convincing evidence. That's usually how they say that. We have convincing evidence that the computer program is flawed. That probability is so low. So the fact that it actually happened tells you that something is wrong with the computer program. Since it's such a low probability, that shouldn't happen. You should have more people who are drawing a 3 out of 250. So that tells you that something's up with that. All right, this is taking us to the end of our first part of section 6.3. Thanks for listening today. We're going to continue on for 2 more parts, so stay tuned for that. If you have any questions, let me know, and thanks for tuning in.